My name's Elaine Eisenbeis. I'm the owner and principal statistician here at Omega Statistics. I want to thank all of you who took the time to join me here today. Today I'm going to present a quick review of Kaplan-Meier survival methods and then an overview of Cox proportional hazard models, also called Cox regression. And we'll have an example in SPSS of the regression. The idea for this webinar was suggested by one of our regular attendees, Jerry. So thank you very much, Jerry. Today is just an overview. There's no way I can cover the whole of survival analysis and Cox regression in an hour or so, but I hope that the information you receive today will give you some ideas and guidance on how and why to use Cox regression in your own studies. As I say in all of our webinars, use what you learned today, apply it in a holistic way, and look at that big picture of what you're doing, and that usually will help guide you in what you need to do. I'll have a lot of references at the end that you can go and look at and such. And of course, if you have any questions, I'll try to find you a reference if I can't answer it readily. I am an applied statistician. I don't sit at a university studying books and running simulated models all day. I do get my hands dirty in real data. So I care more about actually running the data and getting the results and not so much on the formulas, which is a good thing for some people and not so good for others. So if you're more of a technical kind of formula person, I'll do my best, but I know what I need to know, and that's about it. Okay, so I always like to take a minute or two to talk about Omega Statistics and what I do. Statistics is a difficult subject. I always say this for even seasoned researchers. And often textbooks, classes, training programs, sometimes they will make things even more confusing. So my goal with the Stats for the Masses series and for Omega Statistics as a company is to inform and educate researchers about statistical concepts. I try to put it in layman's terms as much as possible. And sometimes that isn't easy, but I do try to do my best. And that way, I'm hoping that everybody can see the elegance and usefulness of statistics. So these quarterly webinars are always free, and I do record them. So if you can't make it to the live meeting, you can always sign up, register for it, and then you'll get the handouts and the recording later so you can review it at your convenience. And also, you can go to the webinar page on the Omega Statistics website to view any of the past recordings that I have posted there. We also have a YouTube channel, and I'll send that link out when I send the follow-up email with your handouts. Okay, so our next webinar is going to be in February, and I'm not really sure exactly what I'm going to cover, but Jerry gave me a great idea for this time. So if any of you have some ideas, please share them with me. And if it's something I feel that'll make for a good webinar in about an hour and a half, I'll do my best to present that because I want to give you things that you can use. So a little bit more about me is that well, I do help with dissertations. I also help with clinical research. Those are probably the two biggest areas I do work in. I do help with designing surveys. The past year or so, I have been offering seminars and webinars. I call them off the rack ones that are already made that I present over and over all over the country. I also can do custom made ones. So you can check the website out, look under the events page, the tab on the events, and you can read more about what is being offered that's off the rack. And there's a way, if you want to contact me, just shoot me an email or fill out that form, and we can talk about maybe putting something together for you or your organization. And my motto is to provide elegant solutions effectively applied. So I do that all the time. So here's some things we'll cover today. We're going to go through a bit of history and reasoning for Cox proportional hazard models. And you'll also hear me call it Cox regression. You'll even see me write it both ways. They are the same thing. So don't let that throw you off. I always say statisticians have 5 names for everything. And I don't know if we do it. We don't really do it to confuse people. The reason that we do it is because we do, as John Tukey said, we do play in everybody's backyard. And every discipline has their idea of what they like to call something. So that's why we have those different names. So we'll learn some terminology as we go through the slides. We'll do a quick review of Kaplan-Meier method, the survival analysis with a log rank test. We'll do a review and interpretation of some survival curves, and then we'll look at some assumptions for Cox regression, and I'm going to run one in SPSS, a fairly simple one. Like I said, it's an overview. I don't want to make it too cumbersome or confusing today. I just want you to get an idea of what it's about and why we use it, okay? So here's a quote for today. This is from Fight Club. I love the movie. I'm actually reading the book right now. My daughter's in college, and it was one of her assignments to read the book. And I saw her reading it, and I said, I didn't even know there was a book. I thought it was just a movie. So, but as I was reading the book, it was great because this quote was in there that on a long enough timeline, the survival rate for everyone will drop to 0. And isn't that true? And what we're covering today is survival analysis, and it's usually not about happy things. The biggest survival analysis models are done in oncology, and they're usually for cancer survival. And so I did have somebody ask into questions about, they want to know about life of computer parts or computers. You can do that too, and we'll learn that there are other events. It doesn't always have to be a death. Okay, it's time to event. But since it is used so much for survival and death is your outcome, that's why it's kind of that way, but it is important. So here's some history and background. The seminal paper was by Kaplan and Meyer. It was this non-parametric estimation from incomplete observations. And yes, Kaplan-Meier is non-parametric. You don't need a special distribution for it. Okay, and that's the nice thing about it. Cox regression, when we look at it later, that's called semi-parametric, and we'll go into that a little bit more. And there also are parametric techniques you can use for survival, where you have a set distribution. You know how the rate, the hazard rate, or the events are going to go, what distribution they're going to follow, and then you actually can use a parametric technique. But of course, we won't be going through any of that today. But we will go through some of this. So the KM method is used in more than 70% of oncology papers. The Web of Science citations are up over 44,000 as of November of last year. This paper is the most cited statistics publication in the scientific literature, but it was only cited 25 times in the first decade after it was published. So, it took a while to catch on. And the reason is that it was published in 1958. Computers really didn't start coming online probably until the 80s. As far as personal computers, other computers were around, but not everybody had access to computers like they do now. And a lot of the techniques we use nowadays are very computationally intensive. If it wasn't for computers, we wouldn't be able to do maybe not even a quarter of what we do. Okay, these two gentlemen are very interesting. They did actually collaborate on this paper, but it didn't start out that way. They were both students of Tukey, John Tukey, and they would both talk to Tukey, and Tukey would say, hey, Kaplan would say something to Tukey, and he'd go, that's very interesting. Paul's working on something similar, and Paul would say something, Paul Meyer would say something to Tukey, and he'd go, you should talk to Kaplan, but they really never conversed with each other too much. They never really collaborated. Paul Meyer actually was interviewed a while back, and he said that it didn't start as a collaborative effort. And according to Paul, he said that they were both working independently on the same topic. Okay, they were both working on the survival curve. Kaplan actually beat Meyer to the submission of the manuscript to the Journal of the American Statistical Association. And then so Meyer said, more or less, he was quoted as saying, well, I got pretty mad and I called John. And he called Tukey. Ultimately, I wrote to the editor of JASA about that situation. By the time I had estimated the means and stuff like that, not just Kaplan-Meier alone, and I offered JASA this as a second paper, but the editor of the journal wrote back, and he said, our readers wouldn't like it if you separate this into two papers. I'd rather you both got together and wrote one paper. And so Paul Meyer said, I swallowed hard, and I guess Kaplan swallowed hard as well. So we worked quite hard And at one place, he solved a problem that I couldn't solve. In other cases, I solved problems that he couldn't. So it took about another 4 years or so to put this together. And when you look at the curves, they seem simple, but sometimes a lot of thought goes into it. And collaboration, it's wonderful when it happens in research, and it does happen quite a bit. I'd like to see it happen more often. These two worked it out well. There are other other kinds of times. Newton and Leibniz, as an example for calculus, that didn't end as well as Kaplan and Meyer. And if you ever want to look up Newton and Leibniz and calculus, it's a very fascinating story. But we won't go into it today because we're talking about Kaplan and Meyer. So Cox he's actually he's knighted. He's Professor Sir David Cox. Okay, and he's actually still around. I think he was born in 1924. That makes him about 94. He's been married over 70 years. I think he got married in 47. So I mean, it's just, when I think about that, it's just amazing that somebody's been around that long, and it seems so long ago. But he's still around, and he's written or co-authored 300 papers and books. He's had a book published in his honor. He's actually has a website if you want to go check it out at Oxford. He has his little web page there, and he not only did he do Cox regression, he's responsible for pioneering logistic regression. And a lot of people say Cox regression is similar to multiple regression, like it's a takeoff from multiple regression. But when I see it, it looks a lot to me like logistic regression. So I'll show you that in a little bit, but it kind of makes sense that he would do both. And of course, he made the proportional hazards model, which is Cox regression. He also did something called a Cox process, and that's used mostly in modeling financial risk. And I've never used it, but I've heard about it. And he was an editor of Biometrica for many, many years. So there's his picture there. So we have these guys to thank. So let's go into the KM survival analysis, comparing some survival curves. Some things to know: survival curves plot to percent survival as a function of time. These are what we're looking at today, are always have that time element involved. Survival can be anything. It doesn't have to be dead or alive. Mostly it is, but it doesn't have to be. It could be the percent of patients in remission, so that's a good thing. It could be time until an event like a heart attack, a weight loss of 20 pounds. That's great. That would be nice. So it doesn't always have to be doom and gloom. Okay, so typically we want to compare survival curves of two groups, a treatment and control. You can compare more than two groups, and I'll show you an example where I have a comparison of 5 cohorts. So it doesn't only have to be 2. Okay, we use a log rank test to compare to survival curves, and sometimes you'll see this called a Mantel-Hansel test. Sometimes you'll see it have a chi-square statistic, but they're all names for the same test. Calculations for that log rank test, they're tedious at best. And I always say computers are our friends. And as I said, this is why these have taken off so well, because computers are so wonderful. The log rank test only compares the effect of one variable at a time on prognosis. So if you want to access multiple variables, like say you don't want to just look at whether a person had an event or not, but you also want to maybe look to see if age mattered, maybe a gender mattered, things like that, other variables, which we call covariates in this case, then you're going to use that Cox regression. And again, computers are our friends. So it's always nice to, learn a software or two, learn them well. And I have many softwares I use. I do have some favorites. I love SPSS. If I ever need to write anything, it's nice to know R, because R, if you can't do it in another software, you can always write something. My friend Isabella, who I think is listening, she's probably the best R expert I know. So if you ever need to get in touch with somebody who knows R, let me know, and I'll hook you up. So here's some assumptions for our survival analysis. There's 6 assumptions that we use in the KM method. First one is the event status should consist of 2 mutually exclusive and collectively exhaustive states. So you either have something that's an event, or you have something that's censored, where the event didn't happen. Okay, and the event also can be referred to as a failure, because a lot of times it is based on maybe your computer part going out, or somebody dying. So the event status is mutually exclusive because the outcome for a case can either be censored, which means they didn't have the event, okay, they did not die, or the event has occurred. It can't be both. You can't be both alive and dead. You can't be both lost 20 pounds and didn't lose 20 pounds. You can only be one or the other. So they make it sound really difficult, mutually exclusive, right? But it just means you can't be both, right? You can't be in both groups. Um, I have an example to imagine that we're interested in the survival times of people suffering from lung cancer where the event is death. Okay, so if the length of the experiment is 5 years, at the end of that 5-year period, all participants would either be censored, which means they are still alive, or they would be dead. Therefore, the two states should not only be mutually exclusive, but also collectively exhaustive. That means at least one of these states must occur, right? Everybody has one, they're going to be one or the other. You're not going to have anybody that's still in the study that wasn't coded either as dead or censored, which is censored means alive or the event didn't happen. The second assumption is that the time to an event or censorship, which is known as the survival time, should be clearly defined. It needs to be precisely measured. Okay, so you need to go in with a knowledge of what you're doing and how long you're going to take to do it. The KM method, unlike some other approaches to survival analysis, like there's an actuarial approach, there's other approaches. It requires the survival time to be recorded precisely. You need to know exactly when that event or that censorship occurred, because one of the things you need to do is record the time to the event, right? So you need to have that precise. You can't simply record whether the event occurred within some interval, like during the study. So you can't just say, oh, okay, it happened at 1 year follow-up. Well, between when they were entered into the study and at 1 year follow-up, that's a big amount of time. So we want to know the exact time it happened. We don't want to say at follow-up, oh, they just aren't there anymore, right? Because it could have happened at 1 month, could have happened at 6 months, right? Could happen at 11, right? So you need to have that precision, okay? So in addition, that survival time should be clearly defined, right? Whether this is measured in days, weeks, months, years. I mean, you can measure it any way you want, but it has to be a timed event. Okay, so the third one, where possible, we have two kinds of censoring. There's right censoring, which is what you have for the people who didn't have the event. They never had their death. They never lost their 20 pounds. They at the end of the study, at the end of 5 years, maybe they only lost 10 pounds, so they didn't make it to 20, right? So they're going to be right censored. We didn't follow them all the way until they lost their 20 pounds because we had to end the study. You can't have studies go on and on and on. It's time and money, right? So a lot of studies will go for 5 years, sometimes 10 years. And you might have follow-up, but the actual study is going to be a certain amount of time. So you can have the right censoring, but you really don't want what's called left censoring, okay? Now, left censoring occurs when the starting point of an experiment is not easily identifiable, okay? So again, let's imagine that we're interested in those survival times of people who are suffering from the lung cancer, okay? So the ideal starting point would be to measure the survival time from the very moment that they developed the cancer, right? But we don't know that. It's more likely that they're going to be enrolled as soon as they're diagnosed, okay? Because it's more likely that the first time the participant knew they had cancer was the moment it was diagnosed. And so diagnosis is going to be the starting point for the experiment, okay, not the development of the cancer. So even if we isolated our sample to just stage 1 cancer, there would still be differences between the participants because when you put people into any kind of study, which is most studies are, the human element always adds some extra information, extra problems in any kind of almost any situation because we're complex. Okay, so for an example, some participants may have had a cough and they didn't get checked for some time, right? Oh, it's going to go away. I'm okay. Other participants may have went to the doctor as soon as that cough seemed persistent. Boy, I've had this cough 2 weeks. I need to go see a doctor. So their diagnosis was made much earlier. So therefore, that time between the participant developing lung cancer and the diagnosis is unknown, right? So we don't know when they developed it, but we do know when they were diagnosed, and then we can make that the starting point. So the result is that this data, known as left censored data, when you didn't know when they actually got the cancer, doesn't reflect the observed survival time. So instead, that survival time recorded is going to be less than or equal to that observed survival time. So the goal is to avoid this left censoring as much as possible. So a lot of times you will start them. Another one too is you're accruing patients over time. Say you need 300 patients for your study. You're not going to get them all at once. You're not going to recruit them in a day. You're not even going to recruit them in a couple months. Sometimes it takes years to recruit. So as they come into the study with their diagnosis, that's their starting point. So it's at time of diagnosis, that's when they enter their study. Okay. So you want to avoid that left censoring. Okay. Assumption 4. There should be some independence of censoring and the event. What this means is that the reason why cases are censored does not relate to the event, right? We don't want to, let's see how I would say, for the assumption of independent censoring to be met, this assumption, we need to be confident that when we record that a participant censored, that they didn't have the event, that they went all the way through the study and they were still there, still kicking. It's not because they were at a greater risk of the event occurring, or not at a greater risk. And instead, there may be other reasons why that participant is legitimately censored. Okay, so it doesn't necessarily mean that they they might be censored for other reasons besides just having the event. Maybe they dropped out. There's a natural dropout or a withdrawal. They don't want to take part in the experiment, or maybe they go for 2 years and then they decide, I'm done. I don't want to do this anymore. It's a 5-year study. Well, you have to censor them, and you also have to mark the time that they were gone. Okay. Sometimes the event not occurring by the end of experiment, right? As I was saying a little bit earlier, they go all the way through. If it's 5 years of an experiment, if they're still alive, they're going to be recorded as censored. Okay, so independent censoring is important because the KM method's based on observed data, right? Observed events. And it assumes that censored data behaves in the same way as uncensored data. We don't want there to be differences between the people who survived all through the study and those who didn't. We don't want there to be some underlying cause that's doing that. Okay. If the censored data does not relate to the event, like a participant was recorded as being censored and died due to cancer, or perhaps something related to the cancer, this introduces a serious bias, right? If they're because they're recorded as being censored, but they still maybe they died and it was something to deal with the cancer, but the person who said they were censored and took them out of the study for death for other causes. You want to be careful for that. You also don't want them to be if they die from other causes besides cancer. Oh, heaven forbid they they die from some other cause. I don't know. This is horrible to talk about, isn't it? They get hit by a truck, or something like that. Well, that's not cancer related. So now you're going to censor them, right? You're not going to include them as an event. You're going to censor them. So you want to be careful with that because you don't want to overestimate your survival. You don't want to underestimate the survival. So assumption 5, there should be no secular trends. This is also called secular changes. So a characteristic of many studies that involve the survival analysis is that, for one, there's often a long time period between the start and the end of the experiment. Like I said, these go on for years, right? And secondly, not all cases, not all participants tend to start the experiment at the same time. Okay, so example, the starting point in our hypothetical experiment was when participants were diagnosed with lung cancer. However, it was like I was talking about before. If we need a sample of 500 participants, it's going to take a number of months, maybe even a couple years to recruit all of those participants, and they all have different starting points, right? So we're not making it a calendar time of a starting point. We're making it time of diagnosis entered into the study. That's the starting point. Okay. So they have different actual dates when they were diagnosed as calendar dates, but we're going to pool that starting and subsequent time. So everybody's first diagnosis is going to be time point O. So when they come in, their diagnosis, they come into the study, that's time point O. And then we follow them from there. Okay, that's when we start looking at the number of days, number of months, whatever, until their event. So if over this period of time there's factors that have changed that affect the likelihood of the event, this also can introduce to bias. Okay, I'm going to show you an example in a little bit about what not to do. And so an example now would be that death rates for lung cancer, they may have gone down following the introduction of new drugs. Maybe some other treatments improving the survival rates. And there's a lot of things that are happening now in cancer research where you have that precision medicine where it's detailed to a particular individual with genetics and such. So they're actually training viruses to go and attack cancer. So there are a lot of treatments, and these things could change over that time of the trial, right? Now, you certainly don't want to deny people the better treatments, but you might need to do something about that bias, right? And you can you don't have to shut down the study. There are ways to statistically control for it. I won't go into it today because they are complicated, but you want to make sure that you're not doing things that are going to change that survival over time because you have a better drug or better screening or something like that. Okay. And a final assumption, there should be a similar amount and pattern of censorship in each group. Okay. So the people that are surviving or dropping out or whatever should be the same, similar in each group. Okay. So one of the assumptions of the Kaplan-Meier method and statistical tests for differences between survival distributions like a log rank test is that censoring similar in all the groups. Okay, so this includes a similar amount of censorship per group and similar patterns of censorship per group. So if you fail to meet that assumption, it can lead to false conclusions being drawn. Okay, you might reject or not reject the null hypothesis. You're going to commit those type 1 and type 2 errors a lot more frequently based on your statistical tests, and it's going to confuse because of the confusing differences in these patterns. Okay, so those are 6 of those assumptions, and when you think about them and you don't get too much into the wording of them, they're not so bad. All right, so there are some things I said I was going to tell you about some things not to do. Okay, here's some things. There's 2 big things not to do. Here's the first one: don't do this. Here's an example. I used my experimental topical treatment, right, a nice topical cream, on subjects that had eczema. Okay, so the treatment worked really well on some subjects, and a large percentage of the skin cleared up really nicely, but it wasn't improved on some of the other subjects. Okay, everybody got the cream. Some people really responded well. Somebody did not, or other ones did not, right? So I plotted 2 survival curves. Okay, I did one survival curve for the responders and one for the non-responders. And then I compared them with the log rank test. And boy, I was so happy. I found significant differences between my responders and non-responders. This is not a valid thing to do. The first reason is because there's only one group of patients. They were all treated. Right? I didn't have a control group. Everybody got that topical, they all got the treatment. So I don't have a control. So I don't have 2 groups. I really only have one. Okay, so I shouldn't be using 2 survival curves. Okay. Secondly, the eczema, it could be heterogeneous, which means, subjects who responded, they might have a different reason for having the skin condition, or maybe they have a different type of dermatitis than a non-responder. So we don't know why that might have happened. For this, you would want one survival curve. And if the event was that they had a clearing of their skin, then that was the event. Otherwise, they were censored. Okay, so one survival curve, not 2. That was the big takeaway on this one. Also, you don't want to do this either. Okay, we go back to the assumption 5 that we had on the previous screen. Okay, there's something called Will Rogers phenomenon. Okay, so an example of this is I'm tracking survival of patients who have a particular type of tumor. So I'm tracking those whose cancer has metastasized versus those whose cancer has stayed localized. It hasn't spread throughout the body or to another area. Okay, so the patients with the localized tumors, they live longer, and that's what you would expect because it hasn't spread. During the study, I started using a better scanner. Right? Remember how I was saying if you get a better diagnosis or a better treatment, that could throw things off. So I started using a better scanner to find these metastases earlier. Okay, so this results in a smaller group of patients without the metastases and a larger group of them with it, because now I'm finding them. I'm finding them more, right? So, oh boy, all of a sudden I have all these people that before I wouldn't have found that it spread, but now they're in a metastasized group. Okay, so It's great. The metastases are better detected and earlier, but these patients are still dying faster. Okay, and now they've been moved into the non-metastasized from that non-metastasized group up to the metastasized group. So this is going to make it appear that the non-metastasized group is better than before the change. Okay, while making the metastasized group appear to improve too, because these newer additions have smaller metastases, right? It's spread, but it was found sooner, so they're going to live longer. Okay, than the earlier patients who were all in the metastasized group. So changing the methods during the study actually increased survival in both groups. Okay, so you don't want to do this. This is called the Will Rogers phenomenon. It's because a quote he gave. He said, "When the Okies left California and went to Oklahoma, they raised the intelligence in both states." So yes, we don't want this to happen. Okay, so those are two big things. I'm sure there's other things you shouldn't do, but I've seen these. I've seen this logic in both of these situations, and you have to be careful on that. Well, here's a pretty Kaplan-Meier curve. If you, well, I guess maybe I should ask for questions again. Oh, here we have. How would you handle an improved method mid-study? Glenda wants to know. Um, there are things you would do. You would probably data wise, you would want to track the ones who were under the new method, and you might want to stratify. Okay, you might want to look at your curves before and then your curves after. Okay, the fact. So you would want to code it so that you would know which patients were getting or when it transferred over to the new treatment, right? You're going to probably have some patients that had the old treatment and then transferred to the new treatment. So you'll probably want to weight your analysis in some way. The details would be, of course, study dependent, but there are statistical things you can do as far as weighting, something like that, where you would maybe multiply by some kind of a number or something like that to, on one way or the other, either on the older method or the newer method people. But there are statistical things. But when you're actually running the study, you definitely want to make sure who got what type of diagnosis or what kind of treatment when, especially if it changed, right? You want to put that into the CRF, the forms, the client forms, that you keep. I guess now they're not actually paper; they're all in a computer, but you definitely want to track that. Does that help? Yeah. Reanalyze it type. No, you wouldn't reanalyze though, Glenda. Yeah, well, you would adjust your analysis, right? Like I said, weighting, okay, would be probably the best way to do it. Okay. All right. So now we have this very, very, very pretty curve. Okay. And so let's see. Let's just go through it real quick. I had this in the those darn ratios webinar back in September. I just love this picture. You'll see here, if you look on the slides when I send them, you can always follow these links and you can see more information and where I got the information. Why invent the wheel whenever I can borrow it? So you always see me say borrowed from. So I like to give credit where it's due, and I just love this this chart. Okay, so this is actually done in R. Okay, and so when you look at some of the SPSS charts we're going to look at later, this just runs rings around those. This is just beautiful. So this was a hypothetical study. Okay, it's a randomized controlled trial. Okay, and it was used to investigate the effectiveness of a new treatment for improving the survival of patients with heart failure. Okay, so we had a total of 105 patients that were randomized into treatment, and 106 were randomized into control. Okay, so the primary outcome was overall survival. So basically, they did not have a heart attack. Okay. And did not have heart failure. Okay, so the main result of this trial can be summarized, with this. This is where when you get your hazard ratio, we'll go over these in a little bit, and so I'm not going to go over it too much right now. But what I can say is whenever you have a hazard ratio less than 1 that favors your treatment, that's what you want. You don't want to have a hazard ratio over 1, and you also don't want a hazard ratio of 1. Hazard ratio of 1 means there's no difference between treatment and control. If it's more than 1, that means your control did better than your treatment. They survived better than your treatment. So you want it to be less, okay? So let's see. We had this hazard ratio here of 0.38. And this 95% confidence interval, if you guys are, you should be used to these pretty much. This is our point estimate. This is the number that we came up with from our data. But since we do guess with statistics and we don't know the truth, we're just guessing at this number. And it's a good guess if we do things right. We have to put a confidence interval around it, which means that we said this was the hazard ratio, okay, 0.38. However, if we were to do this study again in the exact same way, we would expect with 95% confidence that the true hazard ratio is going to be in here somewhere between 0.28 and 0.53. So it's still good, right? If I had a confidence interval that had that 1 inside it, then it wouldn't be significant because it would be possible that there was no difference between treatment and control. Okay, so we like this. So we'll look at this hazard rate and hazard ratio with the Cox regression. But what it means is that patients in that new treatment group at any time point during the study period were 62% likely to die. Because what you do is you take 1 and you subtract that 0.38. So that gives you 62%. Okay, and then the patients in the control group. So we can be 95% confident that that true value is lying somewhere between 47% and 72%, right? Because we're going to take this 1 and subtract that from it, and 1 and subtract that from it, right? So we're 95% sure that the patients with the new treatment group were between 47% and 72% less likely to die than the patients in the control group. So we're happy. And now let's look at the actual curve itself. Okay. This is a beautiful way of showing their survival. So everybody starts up here at 100%, where everybody's alive. Okay. And they all came in at diagnosis time. Okay. So that's their time 0. Okay. And then we're going to follow them. Down here on the x-axis is the time. It's in days. Here's 10 years right here. And I guess it went out a little bit further. And here's the percent surviving. Okay, so what you'll do is you can kind of look at any given point in time. You could go up to the curves and see what percent we're surviving at any given time. Okay, blue line's the treatment group, and the green line is your control. Okay, each downward step here. So we have everybody here, and then right about here, right after the study begins. Well, maybe it's a little while because this is a pretty long timeline, right? Here's 906 days here, so you know, after a couple months, they start dropping off. Each step in the lines is an event, which in this case would be a death. Okay, in each group. Each of these little vertical ticks here are censored people. These are people that went all the way through the study. Okay, so they censored out. What else can I show you? Okay, so yeah, the censored again is a patient who did not experience that event of interest. They were alive at the end of the study. Okay, now this can be due to being lost to follow-up, and the study period could end it without an event or because the patients died from an unrelated cause, which we already talked about. Okay, so the number of patients at risk at regular time intervals is shown down here at the bottom. So this is like at time 0. Everybody at risk means you're still alive, but you're at risk of dying. Okay, so we're not saying, you know, we call it at risk. You're at risk, but that's a good thing. You want to be at risk, okay? But you haven't gone yet, right? So here's at the beginning, we had 106 in the control and 105 in the treatment. Then at 2,000 days, we were down to this many in each group. So we lost quite a few here, and not so many here. You know, we were down to 20 already at 2,000 days. 4,000 days, we still have 25 left in treatment and 5 in control. And then by the end of the study, we had two people who still survived in the treatment group, but everybody was gone into control. Okay. It also allows you to this graph allows you to detect the progression of the condition. So you could look at maybe early post-operative mortality or a serious adverse event caused by a drug by the presence of a notable sudden steep drop in survival at any particular point. These guys, they started out and they just kind of steadily dropped off. These guys, they did it here and then boom, something happened here, right? So it could be that you can see right here that the treatment seemed to prolong a lot of people's lives for a while, right? While they steadily dropped off, and then you had some pretty strong survivors down here, dropped off a little more slowly. These ones, the treatment seemed to work much better than the placebo. And then there's a drop off here, but they're still doing better across the board than the placebo. Okay, so we can communicate this graph in various ways. Okay, we could look at median survival. We're going to look right over here. Let me see if I can get my little pen right here. Median survival, 50%. Okay, so we started at 100%. And then a big interest is, okay, at what time did we lose 50% in each group? Well, median survival here for the control group was 906 days. Okay, but median survival for the treatment group, if I go across here to the treatment line, then down, 2,246 days. So they survived much, much longer. Okay, when by the time we lost 50% of them. Okay. So that's something to see. I don't know. Let me see what else I can think of here. Difference. Okay, so we have a difference in median survival. We just take this number and subtract this number, and then we can say that the intervention group or the treatment group survived for 1,340 days longer. Okay, and that's a couple years, right? So that's good. So the proportion surviving at a specific time point. Well, we can say about 45% of the patients in the treatment group have survived for 10 years, because here's our 10-year mark, and we're right about 45, right? So that's pretty good. And then at 10 years, so look way down here, we didn't have, we were way down low at 10 years for the control group, okay? And another way of saying this is that about 45% of the patients in the treatment group have not experienced a death after 10 years of follow-up. Okay, so lots of interesting things you can pull from that curve. Okay, so here's another example. I wanted to show you that you can do it with more than two groups. You don't just have to have a treatment control. You can have more than two groups. Okay, so this is a data set from a tertiary referral hospital. That's a hospital that provides care, a specialty like the cancer treatment centers, right? So you get diagnosed by your doctor, and they say, okay, you have cancer. We're going to send you to the specialty hospital. From a primary care, from secondary care. So this was a data set where the patients all had cancer. It was a cancer treatment hospital, and all stages 1 through 4 of cancer of the larynx and oral cavity and oral oh my gosh, I can't even pronounce that word. Oropharyngeal. What? Head and neck. Okay, well, head and neck cancers. Okay, and they were referred to the CARE Specialty Group's head and neck program. Okay, for treatment during these years. There were 8 years where they were referred in. Okay, but what we did was we split them up into cohorts. Okay, so we had 1,055 patients that were diagnosed and treated at this hospital. Okay, for their it hadn't spread. It was just localized to their head and neck over the 8-year study. Okay, so we had the 5 cohorts. So cohort 1, they came in for their initial treatment in 2002, and then we followed them until 2006, and there were 185 in that group, and then so on and so on. We had people that come in at year 2003, followed them to here, and so on and so on. Okay, so these all add up to the 1,055. Okay, so my research question is there a difference in survival times over the 8-year time frame between those 5 cohort groups? So our study is 8 years, and we have 5 groups. Okay, so and we have our null hypothesis, which means nothing's going on, right? No difference. And then our alternative, which is what we want, right? We want there to be some kind of difference. Maybe we don't, but we want to test for it, right? Actually, this was a data set I had that it was mostly the study was about cost of care. So we were looking to see if maybe changes in cost and care were associated with maybe the survival. Okay, so but I simplified it a little bit for this example. So we had a total of 240 events, which were deaths, okay, and we had 815 records that were right censored. So yeah, they did not die, or there was some other reason they dropped out, whatever, we couldn't follow them up. Okay, so I used SPSS and set the level of significance at 95%, which is what we usually do. So first we like to look at the descriptive statistics. Okay, so this table has means and medians for survival time. So here's all our records that had an event. Okay, and here's all these are the people these are only the ones that had the event till death. Okay, so there were 240 records that had to death. There's our means, standard errors of the means, and we have our confidence intervals. And the median is really what we like to use in these kind of tests, and I'll tell you about that in a little bit as to why. But mostly, if everybody has the event and you don't have any kind of right censoring, you can use the mean. But otherwise, you should really use the median, and you're hoping that at least half of your subjects have had the event so that you can get that median, right? Otherwise, you don't know what the median survival is because you might have, if you still have 60, 70% of the people that did not have an event, you haven't reached your median. So you want to at least get down to 50% that have had the event. Okay, so the median time in months is here. Okay, as you see, the means are higher for the most part than the medians. Okay, and then there's standard deviations, and of course your confidence interval for those. So you can get those with your software and just kind of take a look at them and kind of eyeball it. You can kind of tell what might have happened. And here I have this is what I was saying with survival analysis. We'd like to have the study go long enough so that at least half of the subjects experience the event in a given group to determine median survival. Okay, so if the study ends and we have, say, 60% survival, then some would say median survival is undefined. Okay, there are times that happens. Maybe for some reason your study's not long enough. And you can't have it be long enough. Maybe it's like I said, it's time and money. Maybe you plan to have the study 5 years, 8 years, and oh my gosh, you would have needed it to be 20 years and you just couldn't have done that. Normally you would like to know that up front so you wouldn't bother to do the study, but it is what it is. It can happen. So there are some techniques, again, that can be used to extrapolate median survival by following some distributional assumptions. So you might be able to look at how things are going with the people that did have the event versus didn't, maybe see if there's a distribution as far as the people that are having the events, and kind of use that to extrapolate median survival. But of course, when you extrapolate things, you're guessing even more. You don't know if that's true. You're making the assumption that it's going to keep following that distribution. Things don't always do that. Sometimes maybe it could have been that, maybe they didn't have the event in 5 years, but at 7 years they would have, right? So, and that would have meant that distribution would have changed, that all of a sudden you would have had this huge drop off in survival, right? And you would have a lot of events, but so you don't really like to extrapolate, but people do it. And other times they'll just say it's undefined. Another way to approach this is, for example, a 5-year study with 60% survival at 5 years. We just say the median survival is greater than 5 years. Let it go. So although median survival is usually used, like I said, if the event happens to 100% of the subjects by the end of the study, we could theoretically use mean survival. And you'll see it every now and then, but mostly you'll see median survival because there's almost always censoring. Okay. So here's the example. Here's my 5 cohorts, and they all have their little different colors. Remember I said it's not as pretty as that other one, is it? It's not as pretty as that other graph. So it doesn't make the prettiest graphs, but today we're interested in Cox regression, so I'm going to leave it up to you to watch this video here that walks you through how to do this survival analysis. You can get life tables, you can get all kinds of different information with most softwares. This one is one in SPSS. So I'm going to leave it up to you to watch that video. It shows you how to set up that data. It shows you how to run the numbers, and you can get, like I said, life tables, hazard rates. You can ask for pairwise tests, because the problem with just using the Kaplan-Meier survival is you have this graph and you have significance. You do the log rank test, which is also called the Mantel-Cox. You get this chi-square statistic, and you get it significant. It's less than 0.05. But then my next question is, okay, it's significant. Which ones differed? Did they all differ from each other, or was it just one differed from the others? I can see cohort 1 seemed to last a little longer, right? But is that the only one? So one might have been different than 4 and 5 right here. So you can't really tell that, but you can with the pairwise. So you can use that with SPSS gives you an option called a Wilcoxon test. It's almost like using Tukey's test after an ANOVA. So watch the video, and it'll give you some more information. So before we go into Cox regression, I'm happy to try to answer some questions if you have them on the survival curves, but we're getting ready to do the fun stuff. Let's see here. What do I have? I do have a question. Would you ordinarily break that chart out into, or could you reaggregate cohorts? Looks like 1 plus 2 is different from the others. Typically, Glenda, if a study is set up a certain way, you have a protocol. Okay. So now we're getting into some fun stuff. All right, so some reasoning for Cox regression. Both KM survival curves and Cox regression use time to event, right? Time, it all has to do with time. Examples of when time to events may be important endpoint variables are often the event of death, as I've been saying, but they don't have to be. So here are some different things. Time from entry in the hospital until discharge. Discharge would be your event. There might be people that maybe they don't, get discharged. Maybe that would be a strange one because, well, if they didn't get discharged and they might have died in the hospital, now you're kind of turning it around, right? Because you want your event to be that you're getting out of the hospital, but if you don't, you die there, then that's going to be a censored, right? So that kind of makes it backwards, but you could do it. So your event can be any event that you want, and it's about time to that particular event, okay? We could have a cure of a condition, right? And a shout out to Neil, who asked about time for failure for a computer system. Absolutely. You could do a study on that, and your event would be the failure. So as you can see, like for KM method, all these have to do with time. So a limitation, though, as we saw of the KM survival analysis using that log rank test to check for differences in survival, is that it can't use multiple predictors, right? It can only run with that same single binary predictor. Either they had an event or no event. That's it. We can't look at anything else. Well, Cox regression can use multiple predictors. We call them covariates in the context of Cox regression. But they can be continuous, they can be binary, they can be categorical, and you can dummy code them. I do have a dummy coding webinar. You can go on my website and find it and look at it. It shows you how to do some coding for regressions. Have a lot of things in a Cox regression are like you need to do like you would for a regression. You can't just throw in a categorical variable. You need to dummy code it. So go watch that or read up on dummy coding, or also called indicator variables. But you can use just about any kind of variable as a covariate in a Cox regression. And now your outcome is going to be a hazard ratio, which we'll go over in a minute. The low p-value on the survival analysis only indicates the groups differ. Remember, we talked about that. But Cox regression, like a multiple regression, can tell us more about the ways the groups differ, right? What contributed the most to it? What predictors do or don't have anything to do with our outcome. So very, very, very interesting. Very good. So let's look at this hazard ratio. So first of all, we have hazard rate and we have hazard ratio. Okay, they are not the same. Sometimes you'll have a hazard rate. Sometimes it'll be called hazard, just hazard, and it represents that instantaneous event rate, which means the probability that an individual would experience an event like a death, or it could be a death, it could be something good, right? At a particular given point in time after the intervention, assuming that this individual has survived to that particular point in time without experiencing the event, right? So say they've gotten up to a year. Okay, hazard rate is at time right at a year, assuming they've survived till then. What is the probability now that they're going to have the event? Okay, so that's the thing. This is over. The nice thing about these Cox regression or a hazard ratio versus a risk ratio is that risk ratios, they get confused, but a risk ratio is only looked at after the whole study's done, and you're looking at the whole study all together. Okay, and then you're looking at a risk ratio at the very end of the study. A hazard ratio, it's instantaneous. It's almost like in mathematics when you have a derivative, right? At that where that tangent line hits it, right? What's happening right there? It's like your first derivative, okay? I don't want to get too technical about it. I say I'm not a math person, but I guess I can't help myself. It's in there. But so it's throughout the study. You can look at different points in time, right? And so that's what I'm saying here, that the hazard ratio takes into account both the number of the events and the timing, okay, and not just the end of the study. So a hazard ratio here is a ratio of the hazard rates, okay? So we have a hazard rates in the treatment group divided by the hazard rate in the control group, okay? So I think that's about it for this one. Oh, I should tell you this, a hazard ratio, these are going to be important. I already kind of covered it. For example, if I had a hazard ratio of 0.5, at any particular time, half as many patients in the treatment group are experiencing an event compared with the control group. Remember, whenever we have this, we want our hazard ratios to be less than 1. If a hazard ratio is 1 at any particular time, the event rates are the same in both groups. Okay, and at 2, at any particular time, twice as many patients in the treatment group are experiencing an event, which is usually a bad thing, compared to the control group. Now, we're going to look at it as event being a death, which we don't want. If you turned it around the other way, you might want this to be high, right? So, but most of the time, you're looking at a death or something like that. We don't want the event. It's something that we don't want to happen. Okay, so we want to look for these small ones. The example today will be that way. I mean, I could show a different way, but it's just, why do that? Just know that you could twist it around. Okay, you could even do this, but and put control on top. But why would you want to? You always want to know treatment when compared to control, and that's what you would do here. Okay. When you do evaluate your hazard ratios, I would recommend you also use another measure like the median survival time, overall survival, time to progression, because these factors can provide insights, okay, about clear benefits, like survival time is increased on average by 180 days, right? Like we showed before, where the treatment was a couple years better on their survival, okay? So now, I'm going to show you a real quick example, and hopefully this will help with the proportional hazards. Okay, a lot of questions, a lot of people get caught up on that. I think I did have one person, I think it might have been Jerry, said, how is it possible that the hazards are the same throughout the study? They're not. The proportion is. We want the proportion of the hazards between the treatment and the control group to be the same, not the hazard itself. Okay, so here's an example, okay? The hazard ratio is going to provide that estimate of a ratio of the hazard rates between the experimental group and the control group over the entire study duration, okay? But the hazard rate is the rate of patients experiencing the event of interest over that short time interval within each of the arms, right? Whether you have a treatment arm and a control arm, okay? Now this concept can be illustrated by this hypothetical example that I borrowed from Science Direct, okay? So it's a randomized control trial. It has two arms and a primary endpoint. So during the first week, the rate of patients dying is higher in the control arm. So here they come into the study. First week, number of patients at risk, okay? They had 100 in each group. Okay, now they died during this time period. We had 3 in the experimental and 4. Okay, nobody dropped out, nobody censored yet. Okay, so here's the rate: 0.03 for experimental and 0.04. Now, if we take the treatment and divide it by the control, we get 0.75. And that's the proportion of the rate of patients dying in the experimental arm compared with the control. So this is like our hazard ratio right here. Okay, so second week, we look at it again. Now we have 97 because we lost 3, right? So we have 97 in the experimental, 96 in the control, okay, because we lost 4 before, all right? So we had a couple people that dropped out. So we had some censoring going on. So, but the rate of patients dying is calculated here. 6 divided by 97, so we have 0.06, and here we have 8 divided by 96, which is 0.08. Now, if I take the ratio of 0.06 and divide it by 0.08, it's 0.74. It's not exactly the same, but it's pretty darn close. And we do this over and over, right? At each time, whatever time we're checking, we want this ratio to be the same, okay? The proportion. So it's not that the proportions in the treatment and the control group are the same that are dying. It's that ratio of the proportions is the same. And now that is our proportional hazards assumption. Does that make sense? I was hoping this would be a nice, easy one to kind of get a little understand, because this, my friends, is what proportional hazard assumption means in a Cox regression. All right, some of you guys want some math, right? Cox regression is a lot like OLS regression, but I think it's more like a logistic regression. And remember, Cox did both, right? He pioneered both. So it kind of makes more sense when you think about it that way. Here's our regular regression model. It's additive, right? Most of you have seen this. You're very familiar with it, okay? So Whereas the Kaplan-Meier method with the log rank test is useful for comparing the survival curves in two or more groups, that Cox regression allows for analyzing the effects of several risk factors. All of these variables are X, all these X's are variables. This one you'll see XN, here you see XK, here you see XK. These are the same. These are just the number of variables, okay? So it's just different notation. I wasn't able to match them up, and trying to make these formulas sometimes can be a real pain. But they mean the same thing. It's just the n's and the k's. You can switch those out. They're representative of the sample size. Okay, so you're going to go from the first. Well, no, they're not. They're examples of the variables. So you're going to go from the first variable to the second variable. So maybe this is age, maybe this is gender, blah blah blah, until we get to the last variable. Okay. So this is our OLS regression. I won't go into that too much, but here's the hazard function, the hazard probability of the endpoint, which would be death, any other event of interest, recurrence of a disease, is called the hazard. So the equation for hazard is modeled by this equation right here. Okay, these x1s to the xk's, there's a collection of your predictor variables. Okay, all these guys. And let's see, this here, this is our intercept, okay? And this is H, the hazard naught at time t. It's the baseline hazard at time t. And it represents a hazard for a person with a value of 0 for everybody else. So if these all zeroed out, you'd be left with HT equals H naught t, because everything here would be zeroed. Actually, this would be, if these all went to 0, I guess if you took the exponent of that, it would go to 1, but it would be 1, right? So it'd be times 1, which is this. It's this is multiplicative, right? These use addition. This one used multiplication, okay? So you're multiplying this by 1, so you're just going to get this. Okay, this is this. So it's very similar in a lot of ways, right? So, all right, so I think I already said T is the survival time. And these are our set of covariates, are all our little x's, okay? Coefficients are here. These are what we're multiplying our covariates by, our predictors by, or the little b's, okay? Baseline hazard we have, okay? So we have this, but now we want to get a hazard ratio, okay? So what we're going to do is we're going to divide both sides by this, H naught T, okay? And then that will leave, since I'm going to divide it, it's over here now. We'll move this over, okay? And that leaves this. Well, when you have the little e, and it's usually like e on the calculators, you'll see exp, but it's e, and then your stuff's up here, okay? When you take the natural log of that makes this go away. So I took the natural log of both sides, because if you do something to one side of the equation, you can do it to the other side of the equation. So then I have this. So I divided this by this, and and then I took the natural log here and a natural log over here. So when I did that, that went away. Now we're just like this. Now we're looking more like a regression again. But here we have this ratio over here, this fraction over here, right? And this is why it looks a lot like a logistic regression. Okay, and I'll show you on the next page. So there's our regular regression additive. Okay, here's our Cox regression. Okay, and here's our multiple logistic regression. As you can see here, we have another ratio. In a regression, we have a logistic regression. These are probabilities. So this is the probability of an event divided by the probability of not the event, or usually a logistic is yes or no, either or kind of thing. So it's binary. So very similar. Okay, and again, these p's, k's, n's are all the same. These are just we have p variables here. We have k variables here. This is a number. They're all numbers, variables. So yeah, so there you go. So there's some math, and you can always look up some more if you need to. But we do have some assumptions. Okay, we have it's called semi-parametric, because there are no assumptions made about the shape of that baseline hazard function. However, there are many other types of survival models that are parametric, but we're not going to cover those today. But some of the names, you might have an exponential, Weibull, Gompertz, log normal distribution. The exponential regression model for survival assumes that the hazard function is constant. Okay. Other distributions assume that the hazard's increasing over time, maybe decreasing over time, or initially increasing and then decreasing. So you can have that kind of thing going on. There's even an additive model. It's called Aylin's additive model. It's not used much because statistical software doesn't have ready-made algorithms that you can point and click. There is a SAS macro. I can send a PDF if you're interested. I'll try to remember to send that in case you want to see it. If you love looking at all the statistical math, it's interesting read. I've never used it. There might be a reason for it though. I mean, somebody thought it out. Yeah, so it might be interesting. All right, so let's do an example. It's going to be quick, and then maybe we'll have some time for some questions. Data is from a book called Essential Statistics for the Pharmaceutical Sciences by Phil Rowe, published by Wiley. It's chapter 23. You can get the data here. In this example, the event is death from heart failure. Okay, here's some variables we're including. Okay, so we're not just looking at the event and censored. We have some variables that we're including. Yay, we call them covariates, variables, predictors. Okay, we have their BMI, and I guess it's British, so it's kilograms divided by this instead of pounds. Okay, divided by inches. It's kilograms divided by meters squared. So age and years. Okay, we have gender. We have whether they were treatment of a placebo, they were a control group versus an active ACE inhibitor. Okay, we have the time in months, which we're going to need time, and whether they were died or were censored. So let's go ahead and run this in SPSS and see what we get. All righty. So again, there's our variables, right? Here's BMI, and it looks small. I mean, in America, we're used to seeing like 20, well, probably more like 30, 40, right? Here it's in metric. Okay, here's the age in years. Here's the gender, and these are categorical. SPS, you could code these yourself, but sometimes in a Cox regression, SPSS gets really weird, and it actually likes you to put them in categorically like this and then make them string variables. So you can play with it a little bit and see what works for you. But in this case, we left them as strings. They're just male, female. Treatment and placebo. Active is our treatment. That's the ACE inhibitor, and then our placebo. Here's their time. Okay. Now, as you can see, this first person, he's censored, but he still had the time here. Maybe he dropped out, right? This person died, and they lived to this many months. And this person died, lived to this many months. And this, so even though they're censored doesn't always mean that you went all the way through the study. Maybe you dropped out, so you still have to put that time in, okay? So it's nice to look at the data to kind of see that. So let's go ahead and do analyze. And then I'll go right down here to survival. And as you can see, there's life tables, Kaplan-Meier. There's Cox with a time-dependent covariate, but we're not going to look at that today. But we'll just look at the simple little Cox regression, which will be very nice. And if you're used to logistic regression, you're going to see it's very, very similar when you get the output. All right. So, it's still up here. So what I did was I had time over here. Let me go ahead and put them out here, and I'll redo them again for you guys so you can kind of see how to do it. Okay, so I'm going to pretend like I'm starting over again. All right, so I went in here. I went to Analyze Survival, Cox Regression. So I'm going to move time into the time box. Okay, then for, let's see, I'm going to move died into the status box. Okay, then I want to define the event. And it's going to give me some different ways I can define it. Oops, my little box over here. So it's going to ask me to define it. I'm just going to say the event is died. Okay, that's the category I want to be the event. Okay, and I'm going to click continue. Okay, and let's see, I'm going to move these guys, BMI and age, gender, and treatment. I'm going to put these into the covariates box because these are our predictors. Okay, and then I'm going to click on plots. And now I get this screen. Okay, so I'm going to click survival, and then it's going to give me all these covariates over here. And what I did was I moved treatment over here because I want separate lines for my treatment. I want to see the active versus the placebo, so I put it over here. Okay, and then I'm just going to click continue, and I'm going to click OK, and it's easy peasy. I'll tell you, isn't that nice? So We let it run, and then we get some output. So let me go ahead and pull that over here. And you can always save your syntax if you want to. So come on, run, run, run. Boy, it's taking a while. My computer gets tired. I think I use it too much during the day. By the afternoon, I think it needs a nap. So anyway, here we go. We got our results. So let me go ahead and go through this with you. So first you have your case processing summary. And what that kind of tells you is you kind of want to check this and make sure that everybody's in there that needs to be in there. We had 273 people altogether. Okay. 201 people had the event. 72 were censored. Okay. You can look down a little bit further here. It says censored cases before the earliest event. It looked like everybody got censored before the first event happened. This is just for demonstration purposes. I'm sure you probably wouldn't see that happening. But when you make up data sets, sometimes you make them for ease and convenience. And it's you're not going to sit in there and spend a day figuring out different times and such. So you also want to look at these categorical variable codings. Like I said, you could maybe set it up to go a certain way, but SPSS is happy to do it for you. Just make sure you check and make sure SPSS did it the way you want, okay? Because it is nice enough to code the categorical for us, but just check to make sure the treatment is 1. So here is how it coded. It coded females as 1 and males as 0, okay? And here's how many were in each group. We had 178 females, 167 males. We had 194 that were inactive, and 151 people were placebo, okay? And so we just want to make sure that's correct. And so in our case, go away. So we just want to make sure that happened. And we have the treatment as 1. I like talking to my screen, go away. Anyway, so like a logistic regression, you're going to get some kind of a model that is it's block that always says block 0. And what that is you're going to have this test, or you're going to have a log. It did a log likelihood test, and this is a -2 log likelihood with no covariates. So this block 0 is basically if you just had that remember that the H0 T equals the hazard ratio. So it's assuming that you have no covariates in a model. If you were just looking at that instantaneous hazard rate versus the ratio, okay? And just to see what number you get there for the -2 log likelihood. Then what you're going to do, what SPSS does for you, is enters in your covariate into the next block, which is block 1. First thing you want to do is look and see if your model was a good fit. And that's what this omnibus test of model coefficients does. Lets you know if you had a good fit. So what we have here is our new -2 log likelihood when we put in all our covariates. Okay. And so it's less. It was 1850. Now it's down to 1787, which is a difference, a smaller. It's smaller, and we want smaller. Smaller is better. And then we look to see if it's significant. Okay, and it is. Okay, so in the change from the previous, the overall model is significant now, and the change of adding your covariates versus the no covariate model, just the intercept model only, is also significant. So that's good. We have a good model fit. We want to see p-values less than 5 in our significance. Okay. Variables. Here we go. Here's our coefficient table. Okay. So these are our B coefficients, just like we have in a regular OLS regression. These here, the EXB, you'll usually see in logistic regression output, but in this case, it's your hazard rates. Okay. So I'll explain those in a minute here. We also have these covariate means and pattern values. These are our averages for each of our covariates. And this is the averages for group 1 and the averages for group 2. Okay, and as you can see, they're kind of similar, which is good. But what these do is when we look at these graphs down here, it's going to be taking into account everything being mean-centered. So BMI makes sense, 1.27 or so. Age, average age for everybody was about 59 years. Gender is a little bit odd. Because I think females were 1 and males were 2. Okay, so you have something a little bit in the middle there, right? I think that means there were a little bit more males than females because it's a little bit higher than 0.5, right? If it was a 0.5, then we'd have exactly the same amount of people in each group. But if I look back at the frequencies, yes, we had yeah, one. Okay, males were coded as 0. I'm sorry, and females were 1, and we had 167 males and 178 females. So therefore, we had more females than males. Okay, and then here's our treatment. Okay, and it's the same kind of thing. We had 1 for active, and we had 0 for placebo. So we had more people. I think if we looked at the frequencies again, we had more people in our active group. Okay, so again, it's going to be higher than that 0.5. So I guess a little weird. But let's go ahead and look at this coefficient table here. Okay, we're going to report the SIG and EXP most often whenever we write our reports. Okay, um, what we want to do is kind of look at our little rates here. So BMI. Let's see what was significant. BMI was significant, age was significant, and treatment, yay, treatment was significant, which we really care about. But also age and BMI were significant. So these are hazard ratios. Okay, so the hazard ratio for BMI was 2.397. So that means an increase in BMI of 1 will be associated with a 2.397-fold increase in the hazard. Okay, so it increases your hazard. Okay. Which we don't like, okay? Because you get older, you're going to have more chance of having a heart failure, okay? For age also, BMI, I'm sorry, increase in weight, increase in your obesity, right? So age is the same thing though. It's significant, but boy, it's really close to 1, that 1.033, but there's enough power in there to see it is significant. So the hazard ratio for the age is 1.033. So an increase in age of 1 year is going to be associated with a 1.033-fold increase in the hazard, okay? And then treatment is 0.434. So those receiving the active treatment have a hazard that is only 0.434 that of somebody who's getting the control. So so that's good. That's lower than 1, and that's what we'd like to see. And remember before how I did the computations, you could subtract that from 1 and kind of read it the other direction. But let's go ahead. It gives you some little survival curves too, just like the log rank test. Okay, this is overall for everybody. So you see there's only 1 line. Okay, and it's been averaged out. So it took all those averages that we had from this table up here and took those into account to make our curve. That we call it controlling for the variables. So basically when you control for the variables, you're moving their effects out so you can really just see what happened with the treatment. Okay, and as far as, or see what really happened with the survival rates. Okay, so that's what we're doing here. And as you can see, they started up here at 100%, and then they went down probably, we lost most of them at about 400. So this was in months. It is months. Okay, so this is everybody. Okay, and then the next one is our treatment, which is active, versus the control, which is placebo, so blue. And you can see they both start out, everybody's there, and then the placebo kind of drops off quickly, much more quickly. Active, they still slope down, okay, but they do a little bit better. Okay, these guys drop off faster, and significantly so. Another way to check for the proportional hazards, you can look at residuals, special residuals. You can look at deviance and such to see if your proportional hazard assumptions met. You can do what I did, where I'm looking at each time and just making sure that hazard ratio is similar. Another way to tell is if these lines were to cross. Okay, that means something's going on. You probably don't have your proportional hazards assumption met. Another way would be if one line went down, but your other group kind of went down and then kind of tapered off, okay, and just kind of went straight. Also, then you don't have, but this, you can very, very well see that they're pretty similar, but not absolutely the same, right? But your ratio is going to be about the same. Okay, so sample size would be the last thing. That was a big question. Oh, how many people do I need to enroll in my study to do a Cox regression? So there's Peduzzi et al. And there's also, there was another one, Long, I think. He's in here. I thought, yeah, Long in 1997. Okay. Rule of thumb is at least 100. Okay, so at least 100 overall. Okay, so you'd have 50 in each group. But according to Peduzzi, he gave this as a guideline. He said let P be the smallest of the proportions of positive cases, so cases that reach the endpoint of the study, or negative cases, cases that did not reach the endpoint in the population. So what you're going to do is you're going to look to see how many people went all the way through the study and completed it and didn't die or didn't have the event, and then how many people did have the event by the end of the study. And then you're going to take the smallest proportion. And typically it's going to be the ones that, the smallest is going to be the ones that reach the end point, because probably, over 50% are going to drop out. You're hoping, so you can get that good median survival, right? So then we're going to let K be the number of predictor variables. So in a case of what we had about 1, 2, 3, 4 or so, so you would take that, and then you're going to just do this. Your sample size is going to be 10 times the number of predictor variables or covariates divided by that proportion. Okay, the smallest proportion of one or the other. So here's an example. If you have 3 predictors to include in your model and the proportion of positive cases in the population is the smallest at 20%, then here's what you would need. 10 times 3 divide, so you multiply those, then divide it by the 0.20, you have 150. So you need 150 people. And then if the resulting number is less than 100, increase it to 100. That's suggested by Long. And I put that those references in our reference list. Okay, here's some more references. Here's a great one. I had this, I think, in the last webinar on how to read a Kaplan-Meier survival plot. Here's some other stuff on survival data. These ones by Clark and Bradburn, there's like series of 4 articles. Very, very good. Nice introduction. Okay, very well written, very easy to understand. I would suggest getting those and reading those, and it's very useful. Here's some sample size references that I just mentioned. And I did most things today in SPSS. My favorite website is the Institute for UCLA's Institute for Digital Research and Education. Lots of stuff there on survival analysis and Cox regression in different softwares. This is from them. This is from them. This is from them. This one's MedCalc, which is a medical, people use it a lot in the medical field. It's very simple. It doesn't do a lot of great stuff, but for the medical professionals, it is very nice. It's easy, very hands-on to use. Like I was saying today, it's just a small sampling, what's available. So hopefully you can use these references and you can look some more. And I thank you for attending. Here's some information if you'd like to reach out. Here's the website where you can go and look at the events page and look at the webinar page, and look at some more things. And okay, so I am ready for final questions if anybody has any. Thank you, everybody, for coming. Yes. Oh, Cheryl asked if we get a copy of the slides. Okay, I can see this. Yeah. Yes, you can get a copy of the slides. I will send them. I need to process the recording, clean it up so you don't have all that dead air from me asking if anybody has questions and just sitting there. And I'll make it pretty, and I'll get those slides to you usually within a week. Okay, so you'll have those. And then I'll also hopefully by then know what I want to do for the next webinar. But thank you all for coming, and have a great rest of the week.